Hello, grade 11 physics. We got some dynamics this week. I'm excited to be back, so let's get right into it. What we need to talk about this week for forces, net force, some acceleration off of that, and as well when we talk about some simple free body diagrams. Free body diagrams will be its own video soon. We're going to go back to grade 10 a little and talk about Newton's laws as well as gravity. So if you were in my class for grade 10 science, we would have kind of gone over this, and I'm sure you would have gone over it with Ms. Harms or Mr. Savoy or whoever was teaching as well. But let's go over kind of the three laws again and what they kind of mean, because it's going to be important when we actually get into talking about forces, when I push somebody, when I pull somebody, when something's falling, when something hits something else. What does that mean, and what are kind of the rules around it? So first thing, we have three laws of Newton. Okay, so Newton's three laws of motion. So the first one, we have the law of inertia. Okay, so what does that basically mean, law of inertia? It means that anything that is in motion wants to stay in motion no matter what, and anything that's at rest wants to stay at rest. And that's kind of a simple one to understand in the sense of, like, if I have this right here, okay, it's not moving, it's not going to move, it's not going to magically move, not until I apply a force and hit it, and then moved. Okay, so same kind of thing as if someone were to be skating on ice. If they push off, they're going to continue moving in that same direction for quite a long time, okay? There's a difference though when, like, if I roll a ball on the ground, the ball's not going to roll forever. There's the question of, like, well, why? Why doesn't it want to roll forever? Well, there's obviously some kind of force opposing that, and that's where friction and air resistance and a lot of other things are going to come in hand that we're going to talk about for our forces. But basically, law one, law of inertia, something that's in motion wants to stay in motion, something that's at rest wants to stay at rest. That also talks about direction too. Sorry, I wanted to make sure I meant that in. If I'm going straight, or if I throw something straight, it's not going to turn direction without another force. Now, if you throw a ball in the air and it starts to turn, that's because of wind and actual force by wind. It's not just by itself. So that's the thing I wanted to say. This has to do with direction as well. So something's going straight and then something hits it to go, turns right. That's another force acting on it. Law number two, basically, there's not a great way of saying it, but basically it's the law of force equals mass times acceleration. So if I want to push something that has a mass of 2 kilograms and I want to make it to go a certain speed, I have to give it a certain force. If I want it to go faster, I need to give it different force. And so we're going to be playing with this formula a little bit, and it's a very simple formula. If you want to find acceleration, just bring mass over here. If you want to find mass, bring acceleration over here. So it's a quite easy formula. It's just 3. But as these next 2 or 3 weeks go on, we're going to be putting on different, like, this will be net force, and we'll be kind of adding to it. But at its core, this is a very nice and simple formula. And that's all we're going to be doing this week, is just playing with a simple formula of this. Last law for Newton is every action has an opposite and equal reaction. So if I throw something at the wall, well, why does it come back to me? It's not because that it just bounced off. Sure it did, but what does that mean? What does it mean that it bounced off? Well, I gave a force to this actual marker. It hit the board, and then, well, what happens? How did it come back to me? The board, because it got hit, gives an opposite reaction and hits it back to you, okay? Same thing, if you think of yourself walking, when you go this way, you're pushing technically this way. So I want to walk this way, my foot pushes that way, and that's why I go this way. It's because when I give a force backwards, the opposite reaction is the ground then makes me go this way. Okay, imagine if you're standing on a skateboard, okay, and this table is here. If I'm on a skateboard and I push this way, well, I'm going to go the opposite way. That's because I push this way, the table is actually pushing me this way. So every action has an opposite and equal reaction. And there'll be a couple of little simple questions about that, kind of with like the snow on the boots and a few other things. So those are 3 laws, just a reminder from last year of those 3 laws. And then I want to talk about one other thing here as well. Where'd my... Oh, wait. Oh, wait, here it is. I want to talk about one other thing as well. I want to talk about gravity. And what is gravity? Alright, so gravity is basically, and a lot of people think of it, gravity as a force pulling us down. It is something that's pulling us down because of the size of the Earth, okay? Because of the large mass of the Earth, it has a gravitational field that pulls things in. But it's technically not a force, okay? Gravity does like exert a force on us. Okay, when I jump, it exerts a force to bring me back down. But gravity, technically, at its core, at its essence, isn't actually a force. It's an acceleration. If I drop two things, let's do this. If I drop two things and drop them at the exact same time, okay, depending on what they are, like if I were to give you a tennis ball and a piece of paper, the tennis ball is going to drop way faster. And people think, well, the tennis ball is heavier, it's going to fall faster. If I drop a bowling ball and a cardboard box, well, the bowling ball is going to drop faster than the cardboard box. But the only reason because of that is because of air resistance. If I found two things that are the same air resistance and dropped them, whether they were heavy or not, they would actually fall at the same rate. So if you get a chance to go watch a video called Bowling Ball and Feather Drop, which I've showed to a few of my classes, and maybe I'll link it in. It's a really cool video showing that a bowling ball and a feather can drop at the same rate because there's no air resistance. They go into a vacuum where they suck all the air out, they drop them, and they drop at the same rate. So gravity actually pulls down at an acceleration of 9.8 meters per second. So basically, if there is no air, if there is a vacuum, it would pull down everything at the exact speed, the exact acceleration of 9.8. Okay, and that's going to be really important just for the fact of this. When we go and talk about force equals mass times acceleration, well, gravity pulls on all of us the same. It pulls on me, it pulls on this marker, otherwise it'll drop. It pulls on everything here, but does it give the same force to everything? No, because I have more mass, and it still wants to pull me at the same acceleration. Technically, it's pulling on me with more force than it's pulling on this, okay? And so that's where we kind of get the distance. Like, it's not the same force that it pulls down, it's actually the acceleration. So the acceleration was the same, but it pulls on different things with different forces depending on their mass. So the more mass you have, the more that gravity is pulling down on you with. Okay, and that kind of makes sense in the sense of like, well, if I were to have this little piece of paper, okay, and I put it right here, it's actually not a piece of paper, it's like a napkin. So if I do this, basically there's a force that gravity is extending on this piece of paper, or sorry, this napkin, okay? It's not a big force, it's a marker. Now if I were to try and stand on this, I'm not going to try to, but it would rip. It's because I have more force, okay? So there's a little intro into last year, talking about the 3 laws in gravity. The next 2 videos, I'm going to do one on kind of this little formula again as well, and then we're going to go into kind of simple free body diagrams that talk about net force and how that works. So cool. Have a great one, guys.